Lesson 10.3, Magnetic Force on a Current-Carrying Wire. So moving charges experience a force when they're in a magnetic field. Well, a current in a wire is a moving charge. Therefore, a wire with a current in a magnetic field should experience magnetic force. Follows the right-hand rule. Remember, the fingers go in the direction of the magnetic field. The thumb points in the direction of the wire, of the moving charge, the current, and the force on the positive charge is up. Remember, our current, our expected current, is moving positive charges. So if we're using that current, our conventional current, then our palm will point the force on the wire. So we had this for the force on a moving charge, QVB times sine of theta, where theta is the angle between the moving charge and the magnetic field. If I divide by t, because current is charge per time, I also need to multiply by t. So I both divide and multiply by t, so I don't really change anything. And q over t is I, and velocity times time is L. So if I replace that, I get force on the wire is current times the length of the wire times the magnetic field times sine of the angle between the wire and the magnetic field. Speakers have a coil of wire attached to a comb that is enclosed by a magnet. A varying current runs through the wire. The current in the magnetic field makes the speaker cone move back and forth. So in the second picture here, you can see the current up here in this top portion is going into the page. The magnetic field is going up towards the top of the screen, so use your right hand, put your fingers pointing up towards the top of the screen, and your thumb needs to go in the direction of the current, which is into the screen. So your fingers are going up, your thumb's going into the screen, your palm should face towards the right. That is the direction of the force. So your fingers are going up this way. Use a better color. Fingers going up that way. Your thumb's going to be going directly back into the page. So your palm would be facing that way. On the bottom, the current's coming out and the magnetic field's going down. So your fingers are going downwards. Your thumb is coming out at you. And your palm would be facing that way. Your palm is facing that way. So the speaker's forced out. Then if the current reverses direction, it'll be forced in. And that forcing the speaker in and out causes sound to be created. Another application of this is Hydrodynamic Propulsion. You will watch the movie Hunt for Red October. It's an old movie. The Russians have developed in that movie a silent running submarine. So Americans are very scared of it, and it uses this magnetohydrodynamic propulsion. What happens is it's a way to propel a boat with no moving parts, hence it's quiet. So seawater enters a tube right there. In the tube, there are electrodes that run current through the water, so you can see the currents going that way. And in the tube is a strong magnetic field. That magnetic field they have pointing upwards. If we use our right-hand rule, we can see the force on the current, which is the seawater. So fingers are going up and down the direction of the magnetic field. The thumb is going the direction of the current, and you see a force. So we have magnetic field, current, palm points the direction of the force. And so that's the force on the current. So that pushes the water is allowing the current to flow, so it actually pushes the water back towards the back of the boat. Newton's third law then pushes the boat forward. A 2-meter long wire is in a 2 × 10⁻⁶ Tesla magnetic field pointing into the page. It carries 2 amps of current flowing up. What is the force on the wire? All right, so my magnetic field is going into the page. Current is going up. So if I use my right-hand rule, my fingers are going directly into the paper. My thumb is going up, so my palm is facing towards the left. So the force is the left. Again, fingers into the paper or into the screen. Your thumb's going up, and the force will be towards the left. Force for a wire, current carrying wire, is ILB sine theta. So I is 2 amps. Here's our I. L is 2 meters. There's the L. And the B is right there. That's our magnetic field. And then we need our angle. Well, into the page and straight up is 90 degrees. So our angle is 90 degrees. Sine of 90 is 1. If you multiply all that together, you get 8 × 10⁻⁶ towards the left.